Hi, my name is Clayton Tobin, and today I'll be sharing the in-body approach to the traveling salesman problem. So what is the traveling salesman problem? Well, here we have an example. Given a list of cities and the distances between each pair of cities, what is the shortest possible route that visits each city exactly once and then returns to the origin city? So here we have an example with 5 cities, and 5 cities have 12 routes. Here we have 25 cities, and it has 310 sextillion routes. Our approach adds an attractive and repulsive force to each pair of cities. We create an outer circle around all of our cities. We put another circle with a radius of 0 inside of the bigger circle. We then expand our smaller circle, and it will push the nodes until all of our nodes are touching the outside of the circle. We then return all of our nodes back to their original positions, and that gives us our path. You can see an example in the bottom left corner. Then we added in pressure. We had a problem where if we had too many nodes, our nodes would get pushed to the outside and there would not be enough room, and they'd start jumping all over on the inside and outside of our ring, and we would not get a nice path. So we allowed the outside circumference of our larger ring to expand. And by doing that, that would create enough room to allow all of our nodes to sit nicely on the ring, as you can see here. Here's an example with pressure and without pressure. As you can see, the without pressure has a much higher percent difference than the one that's adjusting for pressure. Our percent difference is the difference between our path and the known solved path for this problem. Then we took into account for density. When we had high dense areas and we'd expand our inner ring, the high density areas tended to stick together, and they would stay together as they went towards the outside of the ring, so we'd have large clumpings on our rings. In order to solve this, we gridded off this area, and the lighter the grid is, the more dense it is. And we put more circles inside of those denser areas to help expand out the high density areas and to get a more uniform distribution. Here you can see some example runs of without pressure and density, adjusting for pressure, and then accounting for density. And as you see, as we go through each of these, our percent difference gets lower and lower. Our bubble's always better though. We discovered that if you have a fairly uniform distribution of nodes, adding in extra bubbles can actually reduce the efficiency of our algorithm. As you can see, when we count without pressure and density, and then we go to just pressure, it decreases, but once we account for density, it actually goes back up again. These are my sources, my acknowledgments, and thank you for your time.